Hello, we're starting with assignment 4 Q learning, this session, reinforcement learning AI course at the University of Memphis. So, in this assignment, we will solve a classic control problem called mountain car. For more information, you can go to this link and see more about this privacy error. So, maybe not go to that link. And then we want to use Q learning algorithm to solve the task of allowing this mountain car, to learn its way up the hill. And after training, it can go up and reaches this flag here. No. So in the first place, the required libraries are imported. I'm sorry for the interruption. And the environment has been made from GEM, Mountain Car version 0, which is the one we're using here. And the point is that we want to so here is the environment, and the agent is a mountain car. The environment gives us observation and reward and punishment to the agent, and the agent takes an action based on those, and this loop keeps going on. The possible actions we have is to push it left by 0, push right, no push by 1, and push right by 2. So these are the actions that the agent can take. And by pushing itself and gathering reward and observation, it wants to reach out to that goal. And what we can observe includes the position of the vehicle and its velocity. So the way the reward is being defined is -1 for each time step that the agent spends in the environment until the termination of an episode. The goal of the agent is to solve the task as fast as possible, so the reward would be maximized. And the termination includes when it reaches that flag. So the other terminology includes the step, which uh, includes each every time the agent takes an action. And then done is when the flag of the termination of the current episode reaches. Done is true, and otherwise it should be false. So we're moving forward for running the program by running whatever isn't here. Maybe it's the best idea. And we defined the environment before, so we take a random action to see how it works. We take a sample of environment that actions paste the sample, and environment that reset gives us the initial position and resets the environment to its initial situation. And then we can take that step to using this random action and see what is observed as the position and velocity that we talked about, how will it change, and um, what would be the reward, and if it's done or not. So here we can see like the observation, the position is -0.5, considering that I believe environment.reset initial pose would be 0, I believe. Oh no, and we're printing the initial pose to C. Oh, I think because I ran all, it keeps like training, so it takes a while. It doesn't matter. So observation shows that took action 0, which pushes to the left, and by so the position becomes -0.5. It looks like it moved left, so the x is a negative, and the speed is very slow still because it's uphill. If you look at that, maybe that's my understanding. If this is 0, this is the initial position, then moving left wouldn't make the speed so much. And the reward is -1 because for each time step for the reward is -1, and it's not done. It hasn't reached the flag yet, so it's false. And number of actions that can be taken. So right now are three like left. So these are the environmental action space that n that shows how many actions we can take right now. And if the observation has an and the limitation of the observation includes negative 1.2 for the maximum value. Um, so there should be space that high zero. This is just the position that is given to us. The position, the highest value, the maximum would be zero point 0.6. It's the upright uphill here. And then the position, minimum position would be negative 1.2. And this is the minimum speed, but the maximum speed is not printed here. If we want to see that, we might do this. I'm not sure. Maybe there is something wrong that we cannot see it. I cannot run it right now. Um, so the first thing we want to do is that this position space is continuous. So it ranges from negative 1.2 to 0.6, and it's like a continuous space. But because it's very hard for us to keep track of a continuous step environment, and it makes the possibilities so high and the number of actions taken. So it's like increases dimensionality, and it takes a lot of time for us to process. So we want to discretize it to a smaller discrete environment so that we can uh, keep better track of it. So we want to say let's have 20 different positions in this range from minimum and maximum, and 20 different velocities between minimum and maximum. And we use the lean space to do that for us. So this is minimum and then maximum, and the number of positions given. And the speed seems to be zero point 0.7 as the maximum speed. Um, that we cannot see here, but it should be it. And now I think why I know why. I just figured out something. If I was, I would put like dot high here instead of actual numbers, and then dot high one here, and this might be helpful in some cases, but because right now I cannot run it, we cannot see. But it shouldn't be so different. Like it's just a few decimals added. Okay, then I'm interested in running this again. Maybe later we can see the results from this part. And next, we want to see this space discretized. So we print it out like negative 1.2, then negative 1.1 is the next step. These are the steps taken by the lean space. Okay. By the lean space, so that we can see how it's splitting the environment to discrete values. And then, so that we made it discretized, we want to keep track of the observations by um, so it's like we want to make it a combination of tuples beside each other, the tuples of position and velocity beside each other. So for each position in the number of positions range and each velocity in the number of velocity range, we add the position and velocity to the list of observations. So it's like we are generating our own observation instead of the observation from the step function. Our own, which is discretized and is saved here in the observation. And then Q table is the table of Q values for different states and actions. that initially should be zero. So it's like empty, an empty dictionary, and for each state is in the observation tuple, and for the Q table of each observation that includes the tuple of position and velocity, the action given the action that is in range 0, 1, and 2, we initialize the Q table to be 0. So it will look like something like this, that initially each of these Q values are 0. So the observation includes position and velocity. The action includes these three different values, and for each of them, there is a different Q value that is going to be updated as we train through the Q learning process. And that should be it. The length of observation, we can see how many observations we have, because we have 20 velocities in 20 different positions. It would be 400 overall observations, and that Q table length would be 1200, because there are also three actions added to these 400. Okay, we would be able to also print the Q table, but I was impatient and I ran everything immediately. But that's going to be good, because later we don't want to wait for the training process. So in the next place, we are going to define some helper functions, make discrete that does all of these things immediately for us, digitize it. So this is another function we can use to make it discrete instead of linear space, and then return the position and velocity as observation. And then get greedy action is useful when we want to see and each state which action will give us the best Q table, Q value. So it takes the Q table and observation as input, and the actions that are by default 0, 1, 2 for this case, but so it can be used for other environments as well, and we can pass other actions to it. But in this case, the actions are these ones. So it's defined as default, so that we don't need to pass it every time to it. All of the actions are these, and so the values of the Q value, we want to see them, but for each observation given and the action for each action, and for the entire observation list. Oh, this observation is not the entire observation list. It's the observation of current state. So it's like current state or given state to this function, that in this state and all of the actions, considering all of the actions, let's see different values, which is numpy array, and let's see which action is giving us the highest value. So it's argmax of that values that gives us the greedy action, and then it returns that action, because we want this value, this action, to be used in the Q-learning algorithm later. So exercise 1 gives us, please complete the code select action. Here is the code select action. It takes the current exploration rate, which is like the I believe it should be the epsilon value for the, yes, the epsilon value for the epsilon greedy algorithm, and then the greedy action. So there is a random number that is selected between 0 and 1, which it makes us the epsilon value, and we want to see that, which makes us the value that wants to be compared with epsilon. So if this value is smaller than epsilon, let's take a random action. Otherwise, we want to stick to the greedy and choose the greedy action that has been passed to this function. So it's like epsilon greedy, we had this before, and a random dot choice chooses between these three values for us. It chooses the random action. I'm wondering, would it be possible to use this instead of that? this one here, environment dot action space dot sample, that gives us a sample, random sample of the three actions, which is 0, 1, or 2. I think it could also be used in here, like, but I've never tried it. And that's and that, I forgot that, action space dot sample. So I would like to try it later, but but the point is that I need to pass the inf to it if I want to write a good code. So maybe this is easier. Anyway, so here is a function. Exercise one is done, and then we want to define some initial values like the epsilon for the beginning and the decay rate for epsilon, how it changes along the time, how it gets smaller, and the minimal value for epsilon would be 0.01 in this case. Mm, these are initially defined and can be um, fine-tuned later if it doesn't work properly. And then also the environment parameters would be maximum episode steps, that here is 1000 and 50,000 maximum episodes is defined, and the learning rate would be zero point 0.1 for the Q learning algorithm, and gamma is also a parameter in Q learning algorithm. We will see it in the next exercise. That is 0.99 in here. So here's the algorithm. You can see uh, the pseudocode tells us the step size alpha, or this learning rate, should be chosen between 0 and 1, which in here is 0.1. And if we want to choose a small value of epsilon greater than 0, um, and we've already defined epsilon initially, and then we want to decrease it later. So we initialize the Q value, which has been 0. We defined it previously, Q table, for all states and actions arbitrarily, except that. So it asks us to define it as 0, except for the terminal value, but we set it all to 0 and it works. But we can also try initializing it by arbitrary values, which is given by these Q-learning pseudocode. And then we want to loop over for each episode, initialize the state, and then loop for each step of episode. So for each episode would be steps per episode are these for 1000. So we will have this 1000 looped in within this episode, 1000 steps in each episode, and then choose the action from states using policy derived from Q. So this is the one that gives us the action. We should use this select action function, I believe. And then we want to take that action and observe the reward and the next state information. Then given these next state information, you want to update the Q values, Q table, by adding whatever the Q table was. We are adding a learning rate times this value in brackets. That for me is like reward plus an error between the the best possible Q value for the next state minus the current Q value of the current state and current action. So it's like maximum gamma is like um, weight we give it, and the maximum value for Q table given the best action. Oh, okay, the action that maximizes Q uh, in the next state. So if you remember the function here, let's go to get greedy action. We pass it all the Q table, and the next state info, so S prime, whatever we have, we pass it to it, and then it gives us the best possible action that maximizes the Q table in the next state. So here is what happens. This term in here times gamma minus the q value of current state in action plus the reward. So this is the way the q table gets updated. And alpha is the discount factor of the learning rate here. We want to implement this, and it's so the part that we need to pay attention is this part that we have here. So it's just still running. You can see the training hasn't been finished, even though I started it like minutes ago. And so current exploration rate would be the start epsilon, and then reward is empty in the initial state, and the start time is captured to see the time it's taken us. So for all of the episodes, we define like 50,000 that we had. Uh, Time step is initially zero for each episode, and the score is zero, and done is false because it hasn't been finished. And then um, we want to see current observation would be when we reset the environment at the beginning of each episode, and then make it discretized by the make discrete function. So it says while not done, but I believe there should be. Okay, we can check it out later. So let's keep training until it finishes and finds the done turns true. But we can see when done turns true in this code. So we take the greedy action, but get greedy action that we had given the Q table and current observation. And the action would be selected by giving the greedy action and current exploration rate to the select action. So current exploration rate was our initial um, epsilon, but then it's going to decay by the epsilon decay factor. We pass it to the select action, so it goes to epsilon greedy. So the action might be greedy, especially in the first step, that the exploration rate is oh not greedy when the exploration rate is so high, it's 1 initially, but then it gets greedy as it goes by. So we choose the action and then take this step toward getting this action, which gives us the observation, the reward, and done. But the observation given from the step function is continuous, so we again need to discretize it inside of the for each step taken inside each episode. In the next action would be so we want to get greedy action is like the same as this one, but the instead of current observation, we pass the next observation to it, which has been has been taken from this function here. By taking the action, we it looks like we go to the next location, and we want to see how next location would give us the next greedy action. And to update the Q table, so we pass it the current observation of you see here and the formula. So the current observation, the current action, but only for the second term inside the bracket, we need to use the next state and the greedy action for the next step. So current observation, current action is equal to, or easier to say, let's do this, plus equal to, adds to itself the learning rate was alpha times this whatever was inside this bracket. The first term would be reward that was taken here, and then gamma times the Q table for the next observation as we discussed, and the action the greedy action of the next level minus the Q table of current observation and current action. So this looks like an error term here. Show how different the next Q value would be different than the Q value of the current state. And then we increase the time step each for after doing every all of these things inside the loop, and add a reward to the score. We want to see how a score is it increasing, decreasing, how is it changing along the time. And so then we want to move to the next step. So at current observation and will be the observation of the next level. And then for each 100 steps we take inside the episode, we want to add the score to the reward collection so that we can plot it later and see how it changes along the time. And also we need to update the current exploration rate, which is the current exploration rate would be the maximum of the epsilon minimum value for the epsilon, and the current decay exploration rate times the decay factor. So it's like let's decay it, let's make it smaller. So it was initially 1, and then we multiply it by the decay factor to see how it changes. But if it's higher than the minimum, so let's keep it. But if it's not, we don't want to go below minimum, so keep it to be the minimum. So that's why we have this function here, just to update the epsilon value for the epsilon greedy algorithm, and then we write info of the time. Like, so here we can see, here also we're printing like which episode we are in and what would be the exploration rate and the time step and the score. So here is what we can see. Episode Each episode number, exploration rate, completed with completed this time step. So for each of them the time step would be different. uh, it looks like in this time step, for example, this one has been done, and the done will be given. So the loop will be ended whenever this done gets true, which is here, whenever the agent reaches that flag. But we could also add another term, either done gets true or we reach the maximum episode step, which is 1000 here, so that it doesn't go beyond, it doesn't get inside the loop within itself if it doesn't reach the flag. But uh, keeping learning this and seeing the results show that before 1000 steps it always reaches the flag, so there is no concern in that case. And then we can plot how the score is changing, but I'm still waiting for the results, and we're in episode third. Oh my goodness, it's a lot left. And I hope it's fine, but we can take a look into the reward collection. Oh, okay. And we are going for a scale times 100. So in this plot, it's going up like this. I remember I had a better plot. If I can open mine. A for learning, this is my code because it has been drawn before. We can look at that. And going up, the reward going up as for each episode as the episodes go by. Still negative for all of them, but it starts from a very big negative value, and as it learns, it gets smaller and smaller, meaning that we are training well. Otherwise, so it's good to look into it to see if we set all the parameters correctly and if our network is working. And here is the result I was getting. But I reached a good result after, like, okay, so after 2K, I reached a good result. I wasn't sure if I want to continue it or not. But over there, we're going for 50K, and we want to see how it is different in this one. Because this doesn't uh, doesn't work with the while done function. It loops within the maximum number of episodes per time steps per episode. So the only thing remaining is to watch the video. Okay, yes, is to watch the video. That it only happens if it reaches 50,000. Um, I'm not sure if we can wait that much or if I can trim this video and see the remaining later. But I think it worth it to try. And then the next step would be to see how it actually is training by looking at the car during its training process. And I think it's fun, so I want to give it a few minutes to be done and we can watch it together. Any questions meanwhile? Okay, let's see what else we can have. Or not. No, nothing. I think 50,000 is pretty much big. We might not need that if we even look into this plot here. We see that from 30,000, then it keeps like just fluctuating around the same value. So I think 50,000 is pretty much big. I should have changed that, but we just have 5,000 left, so it's better to wait and see. Mm. And I guess I'm going to crop these parts of the video, so don't worry, you don't have to listen to this bullshit. Um, I know I'm so funny, everyone tells me. Okay, 3,000 left. Do you think I should be a streamer or a YouTuber someday? Do you see that in me? Will you be my follower or subscriber? Just let me know. Um, I have things to share. I have interesting things to share. 1,000 left. Okay. Um, I don't think anyone ever watches this. Like, I'm just sharing it to get the grade, but I don't even think the TA watches this, you know? And it's done. Let's see the video. Okay, so here is my plot. In I think if we change some parameters, it might go better. Anyways, and okay, it's still not working, or is it? Let's see. So it says the increase in the reward collected per episode as the episode progress is a good indicator that the agent is learning. Lastly, let's use the code below to render a rollout of agent performing the task. I'd like that. So let's wish this together. Ooh, yay. Have a good one.